Okay, thanks again for joining us. This is module 4 of our virtual power monitoring seminars. And we're going to focus on harmonics today. We're going to talk about the standards. We're going to talk about measurement techniques. We're going to update you on the standards and introduce some new terms and concerns in the industry about harmonics. We're going to talk about some rules of thumb, maybe looking at some of these data, the data and the harmonic content and letting you know whether it's a concern or not, whether it's even or odd order. We're going to also take a little bit of time on our Dranetz software and show you some of the harmonic capabilities of Dranetz, both on a simulation with our harmonics demo tool to look for Triplen and other harmonics and look at some of the theory, but also maybe see some of the advanced capabilities, looking at the harmonic computations that can be done in Dranetz when you have wave shape information recorded by the meter. And that's regardless of whether the meter displayed or triggered or recorded on those harmonic information itself. So let's get started. We're going to kind of do some basics here for some of you, but if you're new to this topic, then this is very timely for you. So the first thing is, what is a harmonic? Well, an integer, a harmonic is an integer multiple of the fundamental frequency. And we're focusing on 50 and 60 hertz systems here. But the principle does apply, but this is the majority, 95% of our customers and our users are working on 60 or 50 hertz systems. And really what that means, what is an integer multiple of the fundamental? Well, the first is that 50 or 60 hertz fundamental. The second, the third, the fourth, the fifth harmonics, again, 120 hertz, 180 hertz, 240, 300 hertz. We're talking about when we talk about 60 hertz systems. And again, doing that math on a 50 hertz system, 100 hertz, 150, 200, and 250. So it's integer multiples of the fundamental frequency. There's something called intraharmonics or interharmonics that are also there and part of the standards, which are frequencies in between these, in between, as an example, at 60 hertz, in between 120 and 180 hertz frequency. So we're not going to get into that level of detail, but certainly the products display that information based upon the standards requirements. So just to put a visual on what a harmonic means, let's just say that you've got two frequency components. Here's your 50 or 60 hertz fundamental. And riding on top of that is that third harmonic. And these harmonics are typically created by the loads out there. Whatever we're plugging into the outlets, they're not produced typically by the power systems out there, although some of the latest concerns have a little concern about some of that. But generically and historically speaking, harmonics are produced by the loads that we plug into the power system, and they interact with the voltage across the impedance of the system. So it's how that, you know, the motors, the PLCs, the very large loads, the computers that we plug in, and it's what they kind of reflect back on the power system. So in this kind of hypothetical system, we have a 60 hertz or 50 hertz fundamental with the third harmonic overlaid on top of that. Okay, that's either 180 hertz or 100 hertz at 50 hertz. And you can see what the result is when you add those two together. So you have what's called the composite waveform. And what we mean by that, that's really what the meter's measuring when you measure the voltage or the current. We tend to reference the voltage for the most part. And really, if you put an eyeball to this, if you kind of visually add these point by point together, you could see the result of that. You could see the impact of that third harmonic on there. So this really visually, this is what happens typically the way meters work. This is what the meter, as an example, is measuring. And the meter does very complex calculations, usually based upon Fourier transforms, to decompose this composite waveform into its individual harmonics. So basically, you get a display like this. I get X percent of the first, the second, the third, the fourth, the fifth. And by percent, usually it's displayed as a percent of the fundamental. So this is what it should be. And I guess I just drew on the screen somehow, for some reason. So this is what it should be, and this is a percentage of that number. You can also display them in volts and in amps and things like that. So there's the ability to do that, or someone else did this here. So you have the ability to look at them both in units, volts, or amps, or the ability to look at them in percentage of fundamental, more of a traditional way to do it. So you have what you don't see here is the first harmonic plotted. And really the reason for that, I mean, in a theoretical system, you should have all the fundamental, 100% of your frequency component should be the fundamental. Well, that's not realistic, but if we did display that fundamental here, it would rescale the screen. You'd have this kind of real big line, and you're looking for these smaller lines. So traditionally, we don't display the fundamental. So you can see the second, the third, the fourth, the fifth, all the way out to the capabilities of the meter, okay? And typically, that goes out to the 40th, or more appropriately today, the 50th harmonic, when we talk about including the number of harmonics in parameters such as THD. So THD is total harmonic distortion. There's voltage THD, which you see, this is a voltage plot, and current THD. The calculations are exactly the same. It's just you have different kind of compliance standards when you come, and look at the results of that. So this is typically how the harmonics are presented, but most people look at the THD, kind of gives you an overall perspective of what the overall harmonic content is of that. Okay, and you can see over here, it's 10, 11% THD is what this is like. And you'll get this right off the meter, right off the software. It's up to you, your preference on how to. Okay, so what are triplen harmonics? Okay, triplen harmonics are interesting, okay, and this is one of the reasons why we have to monitor and measure harmonics. Well, what are they? They are harmonics whose order is a multiple of 3. And we'll talk about that in a second, but the reason why we're concerned is because these triplen harmonics, they add in neutrals. So you can have more current running through the neutral than any one of these individual phases if you have a lot of, or high triplen harmonic content. So we're talking about the 3rd harmonic, the 6th, the 9th, the 12th. All of these things add in the neutral. They do not cancel in the neutral. So that is the concern. Some people say, well, even harmonics don't typically appear in a power system, so we don't count the 6th harmonic, which is not mathematically correct. So we include every triplet harmonic order, multiple 3, 3, 6, 9, 12. Just even harmonics don't typically appear in a properly operating power system. So they're not that big of a concern, but mathematically they're there. And we'll talk about that in a few minutes. So again, you can see the additive effect of them. And this is that image that I showed before. So picture a 3-phase system visually here. So I have phase A, phase B, phase C, and they're offset by 120 degrees, which is, theoretically are offset in a Y system or even a delta, but we're talking about Y in neutrals here. But you can see how visually, you see how that 3rd harmonic, they line right up on top of each other. Okay, the same thing for the 6th and the 9th and so forth. So the vector sum at 60 hertz is 0. The vector sum at the 3rd harmonic is 3 times. So you can see this is the reason for concern of triplen harmonics. And in a few minutes, when we get to the proper point in the webinar, we're going to open up DranView. I'm going to show you the harmonic demonstration tool built into DranView to show you, in real time here, when you add these 3rd harmonics or triplet harmonics in there, the effects on the neutral. So you'll be able to see that. So, okay, we're gonna talk about this at the end. And there's something called the rule of symmetry. And this is what I was referring to before. This is our rule of thumb that we're going to cover today. And that's really, the rule of symmetry really means that even harmonics typically do not appear in a properly operating power system. So why is that? And you can see here, here's an example. I believe this is a current wave shape, okay? And you can see that the positive half and the negative half, they're both dirty. They're not clean sine waves, but they are symmetrical. So take the top half, flip it upside down, shift it 180 degrees. It is identical, okay? So what's happening on the positive side is happening on the negative side. So mathematically, when it runs through the FFTs and everything, when you have this symmetry, only odd harmonics come out mathematically. You'll see a little bit of noise for even harmonics, but they're not a significant component here. If they are different, and you can see here, this is a wave shape with an output rectifier is blown, and I think in this specific one, it's an old UPS system. You can clearly see how the top and bottom halves are not the same. This is asymmetrical, so these are not symmetrical, so both even and odd order harmonics will be produced. So the rule of thumb here is if you see even order harmonics in the typical power system, there's probably something not right there. Now, note that there are exceptions to this. I understand, I think some X-ray machines and medical imagery draw current different in the top half versus the bottom half, so they probably don't apply to this rule of thumb, but traditional power generation and power consumption does apply to this rule of thumb. And the fact, in this particular customer's example, he thought the meter was broken and he sent it in for repair, and we're like, no, there's something the matter with your power system. They did fix it. There was a problem with their power system. So, wrapping it all up just in the kind of the basics of harmonics, when should you be concerned about harmonics? And harmonics are typically considered a problem when they're always present. It's steady state distortion that continuously occurs. And really what that means is that any waveform can have harmonics. So consider a power quality event, a transient, a dip, or a sag in different terminology. Well, temporarily you have high harmonic content potentially. And let's just assume this is one wave shape and then it went to clean waveforms over here. That's not really the concern. You can mathematically look at any waveform, but really you're looking at the cumulative effects of continual harmonic distortion on the power system. That's what provides the issues with motors, you know, creating harmonic issues and overheating in motors and transformers and things like that. It's not that one waveform that goes awry, it's the continual effects of that on usually the transformer and inductive devices, although you can see the triplet harmonic issues on neutrals as well, okay? So again, it's not one wave shape, it's the continual effect on it. All right, so let's change gears here and let's talk about the harmonic standards, both what exists today and some of the more recent changes in the last couple of years and where things are going tomorrow. So when we talk about harmonic standards, really the benchmark in the industry is IEC 61000-4-7. Okay, it's an international harmonic standard that's been used for years. So Dranetz has been applying it in our products since the early or mid 2000s when this became prevalent. It is a part of 61000-4-30 Class A requirements and certification. So our last webinar, we talked about 61000-4-30, which the current edition is edition 3. Well, since edition 1, it called out IEC 61000-4-7 for its harmonic measurement technique. So -4-30 didn't include how to record or measure harmonics. It said use this other standard to do it. Again, -4-7. So basically what this standard does, and in our next slide, I'll break it down a little bit more. It measures harmonics in consecutive windows of 200 milliseconds. Not one cycle, not 100 cycles. It's looking at 200 milliseconds, which at 50 hertz is 10 cycles, and at 60 hertz is 12 cycles. So it looks at those 10 or 12 cycles, and it does the harmonics on that window of 200 milliseconds in time, okay? Now, IEEE 519, which is the US recommended practice for harmonics, got updated in 2014. And that was very important in the United States and North America and other parts of the world who reference this standard. And basically what they did is they harmonized the harmonic measurement and computation techniques with those of 61000-4-7. So in a nutshell, the IEEE said, okay, what 61000-4-7 is good, we're gonna just harmonize with that and make it the same. But they added statistical computations and new parameters on top of that do not exist in 61000-4-7. So in the international world, in Europe and other parts of the world, there's other IEC and other compliance standards that say, okay, we got these measurements from 61000-4-7, this is a pass-fail based upon the type of loads or circuit that we have, okay? And there are IEC standards and other standards for that. Well, in the United States, IEEE 519 took that upon itself when we talk about power and transmission systems, the interconnect between the power producers and the consumers of electricity. So what they did is they specified 3-second harmonic calculations for voltage and current called very short time harmonics. So what that is, it's an aggregation of 15 of these 200 millisecond windows. Our next slide will show that to you. Then they did 10-minute harmonic calculations for voltage and current called short time harmonics. That's an aggregation of 200 of these very short time harmonic windows. So the shortest window is 3 seconds and then aggregated to 10 minutes in 2 different parameters. And they created some limits and statistical requirements for voltage and current for very short time and short time harmonics, where very short time harmonics are looked at over 1 day, and short time harmonics, basically, there's 2 statistical parameters over 1 week, okay? And that's part of a report. We'll show you a sample of that report. So looking at it in just a little more detail, when we look at 61000-4-7, how it measures, again, as I said before, we're looking at a 200 millisecond window. At 60 hertz, that's 12 cycles, which you see here. If this were a 50 hertz example, you would see slightly fewer cycles. You would see 10 cycles displayed here, all right? So again, this is based upon 61000-4-30, or -7 rather. So harmonics and other measurements are computed off of this 200 millisecond window of data, and the results must be reported, and the system must be ready for the next window in time. So what this means, it's gapless. It means the meter must be proficient enough, and when it's Class A, to do the computations on this 200 millisecond window and not miss a beat onto the next 200 millisecond window. So no gaps. There are less capable classes in 61000-4-30 that do allow some gaps, but not Class A. All right. Now, it's very important that the above are all required in 61000-4-30 Class A Edition 3 and also the proposed Edition 4, okay, which means you have to comply with this completely. But as a footnote here, these measurements and these methods for measurements, they do not apply when we talk about sags, swells, transients, and other types of power quality measurements. Transients really aren't covered by 61000-4-30, but you need much higher sampling, or more appropriately, much smaller detail. And we're talking about sub-cycle, sub-AC cycle. And when we talk about transients, we do digitization and recording down to microseconds when we talk about that. So when we talk about 200 milliseconds windows, again, it does not apply to these more traditional power quality sort of parameters. It's just for harmonics and some others. So, wrapping it all up, why are we managing harmonics, and why is 519/2014 so important? Well, in the United States, this is the current recommended practice for harmonic measurements and compliance. So really what the prior versions of 519 were lacking was telling the user, or more appropriately the meter manufacturers, how to do the measurements. So there's a lot of inconsistency in the industry, or one meter manufacturer would do it one way, another one would do it another way, and you take those measurements and you get two different results. Well, that's not good for anyone. So this defined how to do those measurements, and that's 61000-4-7, but also it included the compliance calculations and compliance limits, which are officially for the standard, they're reference to the point of common coupling, the PCC, between the utility and the end user. That's somewhere around where your energy meter is. So that's a good common point of reference. And the applications for this is really being used anywhere in the industry, although this is talking about the point of common coupling with the utility. These are used for individual loads, even though it's not intended for that. People do take this down to the motors, the PDUs, and other places in the system, even though it's not intended for that, just as a point of reference to see, well, what's the harmonic content. So we really talk about modern applications in DER and alternative energy. That's extremely important because utilities and also DER, and DER is distributed energy resources. This is like PV plants and wind farms, things like that. Well, they need to be fairly clean, and the utilities and the interconnects need to make sure that harmonics are not being injected into the utility system, or even vice versa. So it's important to measure there. It's important for utility management. So to have the utility measure and manage the harmonics throughout their facility, and vice versa through the facility. The utility management throughout their utility and distribution and transmission system. But for the facility, they have the same concerns. They need to manage their own facilities, but also make sure that the utility's acting appropriately and they're not giving or sending harmonics the facility's way. So it is kind of a mutual thing. And again, that's why that point of common coupling is so important, because that is that line of responsibility. So if it's upstream from that, it's the utility or power provider's responsibility. Downstream, it's typically the facility's responsibility. So second to last slide on 519, it really looks at both voltage and current, and it's the recommended limits for individual harmonics. You'll see VTHD, voltage total harmonic distortion, and basically they're specified at various bus voltages measured at the point in common coupling. So the acceptable limits are based upon the bus voltage, with higher bus voltages having lower acceptable limit. And there's a very kind of simple way to look at this, where traditionally, or even in theory, the power producers, even if you look at traditional, the coal, the gas, the nukes, they provide produce virtually clean sine waves, okay? Even the alternative energy, PV plants, DERs, things like that, they have harmonic filtering to make sure that they produce fairly clean sine waves. So it's not a transmission issue. Harmonics typically don't originate in the transmission system. As I said before, they originate from the loads that we plug in. The arc furnaces, the individual loads, the computers, ranging from large to small. So when you think about it, the farther you are away from the harmonic generating loads, the lower the acceptable limits are. And the reason being is that they're not being created at that part of the system. So something in the transmission system has the lowest acceptable limit. Something down at the point of common coupling at lower voltage have the highest acceptable limits, because that's where these harmonics are being generated. So hopefully that explanation makes a little sense. So we're looking at voltage harmonics, we're looking at current harmonics. And again, the recommended limits for individual harmonics are specified at different bus voltages for kind of that same rule of thumb. The farther away you are, the lower the farther away you are from the harmonic generating devices, the lower the acceptable limit. So a little bit different here. We're looking at individual harmonics, again, based upon the very short time and the short time harmonics, but we're not looking at current THD. We're looking at something called total demand distortion, not ITHD, current total harmonic distortion. And the reason for that, and we'll touch on this when we get to our energy efficient lighting section, is that ITHD is just a number and it's a percent. It doesn't take into account the size or the capacity of the system. And TDD takes into account the capacity of the system. So in other words, for ITHD, I can have a very, very high harmonic content on very, very small loads in a system. And it's very, very, it looks bad is what I meant to say. So to picture an energy efficient light bulb that's producing some harmonics potentially, it's a very small current. So even in your home on a 15 amp breaker, it doesn't represent that big of a problem. But TDD includes the capacity of the system. So if you have high harmonic or components on high loads or large loads, well, TDD makes that stand out and it's more of a concern. So that the point is TDD must be measured by your instrumentation as well. So again, the current harmonics are measured at higher bus voltages, have a lower acceptable limit. So the bottom line here is that after this was introduced in about 2014 or came in effect 2015, you need a different class of instrument to do this. So some of the older meters on the market may not have this ability to compute. Yes, they can compute harmonics. Maybe they can compute harmonics to 61000-4-7, but you have to make sure they can also apply the statistical requirements of 519-2014. So just verify that with your meter manufacturer. Certainly Dranetz has done that since the introduction of this, certainly in our HDPQ and now our newer Plus family. So just buyer beware, just check to make sure your meter's complete. And this is basically where the pedal meets the metal when we talk about 519-2014. You get a harmonic compliance report every week, okay? So you can see here's the daily report on very short time and short time harmonics you can see, all right? So you can see there's a daily report and a weekly report for each one of those, okay? So every day you're gonna get a report for very short time harmonics. Every week you're gonna get a report for short time harmonics to the 99th percent and to the 95th percent. And these are all called out and specified in the 519-2014 standard. And there's a compliance. It's basically pass-fail. And that's the heart of the standard. It's telling you whether you pass or fail. If you fail, and these are snapshots right from our products, you can see the details in this image behind it. This is the pass-fail. Anything in red was a failure. Okay, you can see the THD failed on voltage. See current's fine, but you can see the failures are here for voltage. Okay, and you can see this on the HDPQ meters themselves and also on the Dranetz software. So make sure that your products can comply with these requirements if you have the the desire or the need for IEEE 519-2014. Okay, so what are some of the new harmonic requirements? All right, as we mentioned in our last webinar, IEEE 61000-4-30 edition 4 is in process and moving towards release. What may have happened since the last webinar is that, and I'm on this committee, is that it was sent out to the individual countries in draft form for their comment. So it was sent, I'm on the US committee and also on the international committee, working group 9. It was sent to the US committee, as I'm sure it was sent to every other IEEE committee throughout the world, and for comments, and the comments are due in July. What happens after that point, it depends upon what those comments are, whether it'll be, they'll have to revise a standard or choose to revise a standard or move towards signing off that particular standard. So that's the particular status or the update on the status of edition 4. Now, what are the significant changes and enhancement from edition 3? There's a whole bunch of, let's say, clerical and minor things. The major things, which we will not get into the details here, is they've changed the measurement method for RVC, or rapid voltage changes, which are kind of small changes and perturbations in the voltage within the high or low limits. It's not a sag, it's not a swell, but it's drifting of the voltage in between there. And the introduction of the Supra harmonics term. This has been around kind of in theory in a while, and this is kind of the first cut of a standard to include that. And what are Supra harmonics? They're voltage frequencies in the range of 2 kilohertz to 150 kilohertz, okay? What are the potential sources of Supra harmonic? And part of the concern is based upon some of these, let's say, newer modern devices, but other devices that have been out there for a while. And basically what this is saying, and we'll summarize this in a couple slides, is that we've been looking up to the 50th harmonic, but maybe there's concerns for higher order frequencies out on the power system. So when we talk about things that can potentially produce those frequencies of concern for Supra harmonics, well, we have the modern IGBT and other inverters or converters for DER, wind, photovoltaic, battery, and other sorts of storage. So basically, in a nutshell, these are DC producing energy sources that must be inverted or converted to AC, and they switch at higher frequencies, maybe 10, 20 kilohertz, maybe even higher these days. And that what happens with that switching frequencies, and those, I won't use the term harmonic, but those frequency comments, if and when they get on the power system. EV charges are also a potential for concern in that, and they kind of do the opposite. They take AC from the grid or wherever the power supply is and convert it to DC at various levels and manage and monitor the charging of, you can see some vans here, or trucks and your cars and whatever it may be. And there's even lorries or tractor trailer trucks that are now, battery based and EV. So also another concern are power line carries and energy meters. This technology has been around for a while. And basically what that means is they don't use an Ethernet or a serial connection. They use the power system and they provide a carrier frequency on that to communicate their data to the kind of the head office. So, and there's other sources that are potentially out there. And when you kind of look at a modern utility system, you can see kind of the concerns for this. And you may have seen this slide before, but when you consider a modern system, we're not only talking about the loads and kind of like the end users of electricity. Well, they too can have, solar, wind, and battery storage. In particular, you can plug your EV into your house and power your house these days. Okay, so you can have those down on the consumer's end of the transmission, or I should say distribution system, but also along the line, going up more closer to the typical transmission methods, you can have the wind, you can have the solar. So these interconnecting, these very high power inverters can transforming this DC into AC and interconnecting with the grid. Well, there are concerns of their frequencies traveling throughout this grid, creating those super harmonics, these higher order harmonics that cannot be measured by the typical power quality meter as specified by 61000-4-30 today. So when we look at it, how do we view harmonics today? Well, we're looking at distortion of 50 or 60 hertz waveforms. All right, we went through that before, beat that up a little bit, but typically that caps out at about the 50th harmonic. So historically, this distortion primarily originates from the loads. All right, it's what we plug into the system. But again, as I said before, this concept is changing a little bit today. So when we talk about super harmonics, we have 519/2014 and -4-7. They focus on 50, 60 hertz fundamentals to the 50th. And where that takes us is to about 3 kilohertz on a 60 hertz system and 2.5 kilohertz on a 50 hertz system. And they measure individual harmonics, or they're included in VTHD, ITHD, and TDD, as we touched on before. Now, to give you some application notes on the Dranetz products, well, we sample and have sampled historically much, much higher than what's required for this 50th harmonic. Okay, so if you look at a Dranetz HDPQ meter, which is our current meter family, they can accommodate higher order harmonics because they sample at higher rates, because the primary thing is to look for sags and swells and transients. And harmonics just come along with that digitization. So what that means in theory, we have the HDPQ family and some of our other products. They digitize at 512 samples per cycle. And what that means, I'll just go back a slide. I take one AC cycle and I have 512 digitized points I use to represent that in the computer of the instrument. So theoretically, that can bring us out to the 255th harmonic, 15.3 kilohertz at 60 hertz for both voltage and current, okay? So that's way higher than the 50th harmonic that is required, okay, by these standards. So you can just see by the standard sampling of our meters, well, we go into the Supra harmonic range and the ability to do some of that with the Dranetz meter that you want today. So really, in theory, it's up to today, before edition 4 comes out, it's up to the meter manufacturer to do something beyond the 50th and what is required by today's standard. So Dranetz HDPQ meters, while we already display voltage harmonics to the 127th and current harmonics to the 63rd. It's not because we couldn't display up to the 255th, but really there's not much use above there until we talk about these very specialized applications that we're now getting into. And quite candidly, it would confuse a lot of the users and make the displays more complex, right? Dranetz 7 can compute harmonics on any voltage and current waveform in the database up to the 256, okay? If your data has that capacity. So when we talk about our older PX5 family, that digitized at 256 samples per cycle. So that can go to the 127th harmonic in theory. But again, focusing on the HDPQ, that's 512. Dranetz can give you any harmonic up to the 256, okay? Actually, 255, because it's usually n divided by 2 minus 1. So n meaning the sampling rate of 512 divided by 2 is 256, minus 1 is 255. So, but again, there's a trend in the industry to capture higher order harmonics than are required by today's 50th harmonic standard. And a recent example is in the UK. They have a fairly new G55 UK harmonic compliance report that's required up to the 100th harmonic. And this replaced the older G54 harmonics, which I believe was up to the 50th. So this requires harmonic reporting up into the 100th or 5 kilohertz. So what Dranetz did, what we recently did to our Dranetz 7 software is add a G55 harmonic report. We did not have to change our HDPQ or any of our other meters to do this because, as I said before, our digitization was more than ample to do this up to 100 harmonics. So what we did is we used the harmonic and time plot calculator capabilities of Dranetz to do this computation for us. And we're going to show you that when we get to our hacks page or hacks section of this webinar. So again, no changes, instant, and what this provided was instant added value to your previously recorded data. So we just provided that in our latest Dranetz 7 update. Well, as we said before, concerns exist with even higher order frequencies that are caused by these high frequency devices or high frequency switching devices that we spoke about before. And really that's where the super harmonics come in. It's super harmonics are voltage harmonics, or I should really call them frequency components because maybe harmonics doesn't work anymore, in the range of 2 kilohertz to 150 kilohertz. Now, new measurement methods are needed, where 61000-4-7, its techniques cap out at 9 kilohertz. Well, you can see we're going beyond that up to 150 kilohertz. So that range between 9 kilohertz and 150 kilohertz, those measurement methods need definition. Well, as part of the committee, and so I've been on the committee for almost a year right now, this is the Working Group 9 committee for the power quality. That's the edition 61000-4-30 committee, working on edition 4. Some of the discussions were the CISPR, the International Special Committee on Radio Interface or Interference. Well, their methods, they do have methods that accommodate this range, but the techniques and the approach is focused on lab measurement. So it but it didn't really apply for field use, but became kind of the fundamental approach of one of the two proposed methods that are out there. So when we talk about this, the term harmonic is kind of misleading, okay? So again, a harmonic is an integer multiple of the fundamental frequency, but we're not talking about multiples of 50 or 60 hertz anymore. We're talking about multiples of maybe the switching frequency of an inverter, an IGBT or other technology inverter, which again is in the 10 to 20 kilohertz range. So these are higher order frequencies that probably aren't based upon any kind of fundamental. So the frequencies are those sources in there, and they're much higher than this 50 hertz. So really what, in a nutshell, is the future PQ meter may become more like a spectrum analyzer than a PQ meter when it talks specifically about super harmonic, where It's just looking for frequency content, not based upon any particular fundamental. So that's kind of where this is heading for the time being. So when we talk about this Working Group 9 committee, they're presently working on, well, what are superharmonics? What are the measurement methods have been proposed? There's actually 2 in the latest version of the standard, in that draft form of the standard that's been sent out to the countries that I mentioned before. And these have been very detailed and complex and sometimes heated discussions, representing both theory and the practicality of making instrumentation and field instrumentation to make this work in the end. However, this is kind of where it wraps up right now. As of today, the superharmonics will most likely be included as an annex to edition 4 of 61000-4-30. Okay, again, it's been submitted in draft form to the countries for comment. Those comments will roll in July, and we'll see how that goes after that. And it's probably dependent on what those comments are and how they've come back. Okay, so again, it's presently included as an annex. It'll be informative and a reference, not a requirement. So it's not part of the body of the standard. It's a desirable and good practice, at least in my personal opinion, that meter manufacturers start including these capabilities because they are out in the industry. And maybe in edition 5 or sometime in the future, this is just my seeing things, that it could be a requirement of the future type of power quality meters out there to accommodate this. So that's kind of in a nutshell what superharmonics are. And I see some questions in the chat. We'll get to them. Do you got anything pertinent to this one? You know what? We'll wait to the Q&A to go through this. Let's just wrap it up because we're getting at about 10 up. So we definitely will attack. Okay, last but not least, okay, before we get into Dranetz, spend a few minutes on its capabilities and then we'll go into the Q&A. So anyway, what we promised you, I think on our second webinar in the series on energy monitoring, we talked about energy savings light bulbs, where we put side by side and an old style incandescent bulb in parallel with a not so old compact fluorescent bulb in parallel with an LED light bulb. And we talked about the energy consumption. It kind of proved out the energy savings claimed by these bulbs, that we're basically saving 75% of the power using. But we left the question is, are there any power quality concerns with this energy efficient lighting? Well, if you look, this is from our Dranetz software, and you can see this is the current of the incandescent bulb in kind of red. This is the compact fluorescent bulb in green. And you can see the blue is the LED bulb, all right? So are there any power quality concerns? Well, from our harmonic perspective, the answer is yes, all right? You look at the next screen, you can see the incandescent bulb at a ITHD of about 3.6%. Now, if you go back, this is not generated from the light bulb. This is just noise in the lab on the power system. So you can consider that pretty much this is resistive load for the incandescent. That's a pretty pure sine wave that we should have gotten if it was isolated from the rest of the system. But you could see how noisy the CF bulb is and not quite as noisy and a problem from the LED bulb. So when you look at the harmonic content, and this is important in the scope of TDD that we mentioned, you could see the ITHD for the incandescent was 3.6% low THD, but you could see the harmonic content, or the current, was a 0.5 amp of harmonic content from this. Okay, this is the 0.5 amp draw, I should say, from this light bulb. You can see the CF bulb pretty distorted, 90%. We did this a couple of years prior to this test, and it was well over 100% the bulbs that we chose. But you could see, look, we're only talking 150 milliamps here. So high distortion, but low current draw. Okay, low distortion, but high current draw for the incandescent bulb. So this is more of a loading problem for incandescent bulbs, not a distortion problem. So this is a distortion concern for the CF bulb, not a loading problem. So you look at the LED bulb, there's more, let's say there's more harmonic compensation in there. We're below 15% current total harmonic distortion, but we're down to 80 milliamps of load here. So basically you could see why we're talking the difference between THD and TDD, where total demand distortion, TDD, would take into account the capacity of the circuit as well. So think of it in our homes here in the United States, maybe on a 15 amp breaker, well, 0.5 amp at a time, each light bulb is gonna add up to something. Just 10 light bulbs is 5 amps already. So that's a third of the capacity of a breaker here in the United States. When you look at an LED bulb today, which I don't even think you can buy CF bulbs anymore, not in the consumer style, but you can see where 80 milliamps is not really a big concern. So a little higher harmonic content, but it's not a big impact on the system when you look at the overall current draw. So just summarizing this, the energy savings bulbs did deliver the energy savings. The CF bulbs was rich in harmonics, greater than 90% THD. The LED bulb was much better, but still just a hair below 15%, 14.5% THD. Well, at the time when we first made the switch over to energy efficient light bulbs, we started with the CF bulbs. There was concern at the times from utilities and other concerning bodies about the mass deployment of these energy savings, or energy savings devices, where the energy savings people said, hey, we're consuming a whole bunch less energy, that is good. Where the utility and the academics basically thought, well, hey, listen, time out. What happens when every light bulb in your home gets changed to this, and every home in the neighborhood or on the substation or whatever? They got to manage this. And really what it boiled down to, it's concerned about the cumulative effects of the large number of bulbs and devices, these energy savings, richer in harmonics. But what it turned out, I don't believe it was much of a problem really because of this. We're just talking about, in our example here, 70 or 80 milliamps or 70 milliamps at the third harmonic, So it looks bad on paper when you look at the high THD, but it's a very, very low current draw load. That's really the difference. So anyway, so let's continue and let's wrap it up, and then we'll get to your questions. And let's talk about these Dranetz hacks that we were talking about. So let me switch over to Dranetz. And guys, did that get shared, or we need to reshare it? It shared? It did share. Okay. Did it unshare? You see Dranetz. Okay, I'm sorry. As a presenter, you don't typically see what's being presented. So let's do a couple things here. Let's show you the Harmonics demo tool, right? And that's a built-in capability. So when I go to View, and I go to the Harmonics demo tool. And what this is, it's a simulator for harmonics. And what it's going to do, it's going to take the current wave shape selected and bring it in the tool. And it gives you the choice to look at any phase. I'm going to look at phase A voltage. Now, what this gives you the ability is to basically put in or out any particular harmonic that you want. So I'm going to reset this, and I'm going to switch to 3-phase. Now, when we talked about triplen harmonics, we're looking at the harmonic content on phase A, phase B, phase C, and its effects on the neutral and its impact. So we said triplen harmonics are multiples of 3. So let's start with something else. Let's go to the 5th harmonic, not a multiple of 3. Now, what this tool lets me do is just, I have a scale here. I can just slide up and down. You can see I just randomly put in 13% on the 5th harmonic. You can see how distorted phase A, B, and C got. There's nothing on the neutral here. Okay, so this is not a triplet harmonic. If I reset this, now let me put in the 3rd harmonic. I'll just randomly put in harmonics. I became distorted on A, B, and C, and you could see the effect on the neutral here. So that is the additive component of the triplen harmonics, okay? Reset again. We talked about before the even order harmonics. Even though the 6th is a triplen, even harmonics typically don't appear in most power systems, but mathematically, it's still there. So you can see I just randomly put in 7%, and you can see its effect on the neutral here, okay? So you can see the 3rd, okay? You can see the 9th. You can see how that adds in, and you can see how that goes up. So this is a visual effect of the triplen harmonics. All right, again, we'll answer your questions when we get to the chat. So this is a very good tool. This is kind of a good teaching tool as we're using it here, and we've used it in our in-person seminars. But also, people who are wondering, well, okay, I've got X% of all these harmonics. What if I filtered them by X%? You could see what the visual effect and what the effect on the waveform are. That's really the intent of this simulator. So just a couple of hacks on harmonics. I have a very simple database here. You may have remembered this from our last webinar. This is what we use for the directivity of power quality events. Is it upstream or downstream? Okay, and you can in fact see that on the bottom, the downstream event that I kind of randomly selected. Just a couple things that you can do with this. Having nothing to do with this, the upstream or downstream. I mentioned before that Dranetz gives you the ability to recompute any harmonics that you have, okay? So I have this window, this yellow out window here. This is the time period that's selected. I make sure on the right here that this is the active window. You can see for active pane, it's got this blue bar around the window that encompasses it. So that's the active pane. I'm gonna go insert, I'm gonna go chart, and I'm gonna insert a DFT or a harmonic chart. So you can see this is reproducing the harmonics that is showing you the harmonic content that's displayed in this wave shape over here, okay? It's showing you exactly what's in here. This is not recomputing anything. This is showing you the harmonics of the waveforms highlighted here. And I can change it to voltage and current. I have all of my properties available for selecting which parameters I want to include. So I'm gonna uncheck B and C, and I'm gonna check the current as well. So I'm gonna say, okay, and you can see how that's changed. Now, one of the benefits here when we spoke about the Supra harmonics, so it's something built into Dranetz when I go to the harmonics in the properties. And by the way, how I get to these properties, either double click on a blank section of the screen or the window, or I right click and select properties is how I'd see it. So I look at harmonic setup here. I can tell Dranetz how far to go out and display the harmonics, okay? So it's taking this waveform and it's computing the harmonics on that waveform. You can see it starts or defaults on the 255th, or the 25th rather. I can go all the way out to the 255th harmonic. I can even recompute THD and include up to X harmonics in that. So if I click OK, this looks much more like a spectrum analyzer now, doesn't it? So it has the ability to go all the way out to the 255th harmonic because the HDPQ, where this data came from, has theoretical capabilities for harmonics up to the 255th. Now, very interesting, I did a presentation at a NETA conference back in February or early March, I forget exactly when, in Denver, and that's the International Electrical International Electrical Testing Association. And someone came to me afterwards when we talked about superharmonics, and they looked at and they noticed that, and I go back here to home and I go zoom, over around the 100th harmonic with their HDPQ, they were seeing some harmonic issues at a solar plant that they have. So this is, kind of a super harmonic concept, and they use this capability in Dranetz to look at the harmonic content out into this area of frequency, okay? So they didn't have to do anything special other than what I just showed you here in Dranetz. Let's take this away. I'm gonna right click and I'm gonna delete it just so we don't clutter the screen here. Oops, I gotta highlight it and then go delete. Okay, so it's gone. Now, when we talked about that harmonic and time plot calculator before, and that's what we used in that G55 report, and that basically says, well, what I did before, I look at one individual wave shape and I put it here and it's a real time. So what I didn't show you before, if I change from snapshot to snapshot or event to event, all those harmonics would update based upon the data that was here in the window, the wave shape. Well, what if I want to be able to plot harmonics and different harmonics than what the meter produced or other parameters? So I go highlight the active pane as the timeline. I go data, and I go harmonic and time plot calculator. And this was part of the advanced Dranetz training that we did. I think it was late last year is when we did it. So you can see, if you look in custom, I have the ability to have Dranetz recompute or compute, if not computed before, from the values stored in the database. And I can just look at some of the basic information here, and that may or may not have been recorded. And we did that the generator testing in our last webinar. That's that frequency that we talked about, where it can look at every cycle in the database and compute the frequency. All right, this is the advantage of that. So the meter did not produce that. But specific to harmonics, you can see we have output options here. Number of harmonics to calculate. And I've already done this earlier. This thing would have defaulted all the way up here to, I think, the 25th probably, okay? You can see I can bring that all the way down to the 256th or 255th harmonic, okay? So what I can do is I can have Dranetz compute those for me. So as an example, if I cancel this out and I just look at the properties here and I go to harmonics, okay, you can see I've got only 5 harmonics that I'm viewing here, the capability, and this is what came from the meter itself. If I go back to this harmonic and time plot calculator and I run this, and I'll just make this a little bit fewer harmonics just to speed things up a little bit. I'll bring it out to the 127th. and click OK. You'll see some windows pop up as it's post-processing the data. Now, if I go look at the properties of the display, just let it, and of course, my Dranetz has a problem here, so just give me a second here. Just bear with me. Sorry, just bear with me 1 second. Yeah, even though I closed some, I got a lot open now. My computer doesn't like that. Okay, so we open this again. And let's go run the, you guys see that? Did share again? Okay, so let's go run that again. And we'll change that, okay, 127th. Okay, you can see that it's done. Right click, properties. And if I go to the harmonics, now you see what else I have here, all the way up to the 127th, okay? And those are available for plotting if you'd like. You can choose any one of these, just like any of the additional parameters that Dranetz could display, the frequency, the power stuff that are recomputed based upon the capabilities that I showed you before, they are available for viewing. So I'll just randomly choose the 25th harmonic. Now let me just shut off this stuff, not to confuse the display. And now you can see it's overlaid on top of that. Okay, you can see right over here. All right. So those are kind of the Dranetz hacks that I wanted to get into here. So related specifically to harmonic. And again, if you'd like to see more, we have our webcast page, and we have a whole presentation that we did live last year that's posted on our webcast page on our website that covers how to do this in greater detail.